Hi everyone, and here's your video for Chapter 5, Lesson 3, Identifying Proportional Relationships. Here are your learning targets and success criteria. By the end of this lesson, you should be able to determine whether two quantities are in a proportional relationship. Success criteria is I can determine whether ratios form a proportion. I can explain how to determine whether quantities are proportional, and I can distinguish between proportional and non-proportional situations. Your vocabulary is proportion, cross products, and proportional. A proportion is an equation stating that the values of two ratios are equivalent. Equivalent ratios such as 2 to 3 and 4 to 6 are equivalent because when you write them as fractions, as you can see, 2/3 is equivalent to 4/6 because you'd multiply the tops by 2. 2 times 2 is 4. You'd multiply the bottom. 3 times 2 is 6. So thinking about what I just showed you, let's think about whether the ratios form a proportion between 6/4 or 6 to 4 and 8/12 or 8 to 12. I can see right away that 4 times 3 is going to be 12. So if I apply that same factor to the top, 6 times 3, I should get 18, but instead I actually get 8. And 8 is not obviously 18, so therefore we would say no, these are not proportional. Let's try 10/40ths compared to 2.5 tenths. And right away I notice that the numbers are getting smaller. 40 divided by 4 is 10, so if this is proportional, 10 divided by 4 would be 2.5, and it is. So we say yes, those are proportional. Now it's your turn. Try it. Tell whether the ratios form a proportion. Show your work, and then push play when you're ready. Let's start with 1/2 and 5/10. 1 times 5 is 5. 2 times 5 is 10. So yes, those form a proportion. For number 2, we have 4/6 and 18/24. 6 times 4 is 24. 4 times 4 is 16, and we have 18 there. So we would say no, those do not form a proportion. 4.5 to 3 and 6 to 9. 3 times 3 is 9. 4.5 times 3 is 12, 13 and a half, and we have 6. So those do not form a proportion. 1/2 to 1/4 and 8 to 4. 1/2 times 16 gives us 8. So there's the math on the side just to prove it. And we need to see then if 1/4 times 16 gives us 4. 16 over 4 is equal to 4. So here we would say yes, those form a proportion as well. Cross products. In the proportion A over B equals C over D, the products A times D and the products B times C are called cross products. the cross products of a proportion are always going to be equal. So you can try to solve proportions in another way as well by using cross products. 6 times 18 equals 108, and 9 times 12 equals 108. So because the cross products are equal, we would say yes, this is proportional. However, I would also like you to notice that there is an easier strategy, and it's actually the first strategy I showed you. You can clearly see that 6 times 2 is 12 and 9 times 2 is 18. So in this case, just looking for that factor or relationship between the numerators and denominators is an easier strategy than trying to multiply large numbers. We have 2/3 here and 4 to 5, and we're being asked for this section to use the cross product strategy. So 12 and 10, those are not equal, so we're going to say no, these ratios are not proportional. Now you try it. I'm going to say that you can use either strategy you want. You can either apply factors to the numerator and denominator, or you can use cross product strategy. And then once you're done, push play for the answers. So here we have 6 to 2 and 12 to 1. Six times 1 is 6, and 2 times 12 is 24. So these would be a no. These ratios are not proportional. And then we have 8 to 12 and 2/3 to 1. So 8 times 1 is 8. 12 times 2/3 is 24/3, and 24 divided by 3 is 8. So we would say yes, these two ratios do form a proportion. And I'd like you to notice for number 6, this is a prime example of where the cross product strategy would actually work better than trying to apply a factor to the numerator and denominator. So just being able to choose which strategy is best is a really important skill here as well. Two quantities are proportional when all of the ratios relating the quantities are equivalent. These quantities are said to be in a proportional relationship. So here's what that means. First of all, an extra vocabulary word is invariant relationship. An invariant relationship is the relationship inside the table between the two numbers. So as we can see here, 2 times 13 is 26, 3 times 13 is 39, 6 times 13 is 78, 10 times 13, that's an easy one, that's 130, and 12 times 13 is 146. So we would say that yes, this table is proportional, and we know it's proportional because it has an invariant relationship throughout all of the terms. So that's one way to tell just by looking at a table whether the relationship is proportional. Another way to tell by looking at a table is by working backwards to see if you have the point 0, 0 in your table. So in this second example, we see that we move backwards by 1, and we go backwards in cost by 75 cents. So let's extend the table. And let's see, as we extend this table, if we end up with 0, 0. If we do, then we prove that it is proportional. Okay, so from 3 to 2, we take away 1. So that means on the other side, we need to take away 0.75. So I end up with $1.50. Now we take away another 1, and we take away another 0.75, and we end up with 75 cents. If we take away 1 final time, we end up with 0. And if we take away 0.75, we end up with 0. So you can see in this table, we end up with the 0.00, meaning that this is an example as well of a proportional relationship. So please note, when looking at tables, you can find an invariant relationship, which is the relationship inside the table between the two numbers, and you can identify a proportional relationship if the table has the 0.00 inside of it. So let's determine whether two quantities are proportional. Here is our table, and we do not currently have an x value of 0, but we could work backwards to find an x value of 0, because what you notice is that on the left side, as we work backwards, we are taking away a half each time. So if we do a half minus a half, we end up with 0. On the right side, we are taking away 3 each time. So if we take away 3 again, 3 minus 3 is 0. If we extended this table, we would get the 0.00, and we could say, yes, this is a proportional relationship. So that is called covariance. How do the numbers change outside the table? How do they change together? Invariance, as we discussed, is inside. 1/2 times 6 is 3. 1 times 6 is 6. 3/2 times 6 is 9. And 2 times 6 is 12. So this invariance shows a factor of times 6, further proving that, yes, these quantities do form a proportional relationship. Tell whether x and y are proportional. Okay, for this first one, time versus distance, this should be a no-brainer based off what we've been talking about. We see the 0.04. That tells you immediately you cannot have the 0.00. And if you don't have the 0.00, it is not proportional. Now let's also look at the invariant relationship to confirm. 2 times 5 would be 10, but 4 times 5 would be 20, and we have 16. So there is no invariant relationship here, and we do not end up with the 0.00 in our table. So 2 ways to prove it, not proportional. In our second table, let's work ourselves backwards and see if we get the 0.00. On the left side, our covariance is take away 4. Take away 4. And on the right side, we take away 2. Then we take away 6. Then we take away 3. Whoa. On the left side, we take away 2. So this is called covariance. And what this shows us is that this function, this proportion, this set of data, it is not even linear. So it is definitely not proportional. And we know that it's not linear because these numbers on the sides, they don't change the same amount each time. They're kind of jumping all over the place. Let's try two more. The number of cases that you order versus the number of rolls of paper towel you get. Let's start by looking at the invariance inside. 1 times 12 is 12. 3 times 12 is 36. 5 times 12 is 60. And 10 times 12 is 120. Immediately, we see that there is an invariant relationship, and we say, yes, these are proportional. If you worked backwards, you would get the point 0, 0, because if you ordered 0 cases, you would have 0 paper towels. For the next example, the number of mules versus bales of hay that you would need. Here we can see an invariant relationship as well. 2 divided by 2 is 1. 4 divided by 2 is 2. 6 divided by 2 is 3. 8 divided by 2 is 4. And 10 divided by 2 is 5. If we worked ourselves backwards, if we had 0 mules, we would need 0 bales of hay. Yes, this is a proportional relationship. Now you try it. Either use covariance, invariance, or find the number 0, 0 to prove whether this is proportional. So for me, I like to go right away to the invariance, and I can see it immediately. 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, and 4 times 2 is 8. So I would say yes, it's proportional, and I know it is because it has invariance, and the factor is times 2. Here we go, let's try another one. Tell whether x and y are proportional here. So let's look to that invariant relationship. 2 times 2 is 4. 4 divided by 2 is 2. 6 times 6 is 1. 8 divided by 16 is a half. And 10 divided by 40 is a fourth. No, not proportional. This is definitely not invariant. And let's actually look at the covariance. On the top, we add 2 each time. So if this is even going to be linear, on the bottom, we should also be adding or subtracting the same amount, and we don't. We take away 2, then we take away 1, then we take away a half, then we take away a fourth. So this is not proportional. It's not even linear. It does not have invariance at all. You swim for 16 minutes and you complete 20 laps. If you swam your first 4 laps in 2.4 minutes, how long does it take you to swim 10 laps? So let's start by comparing unit rates to determine whether a number of laps is proportional to your time. So we'd start with 20 laps in 16 minutes. Okay, so 16 minutes per 20 laps. So if we simplified that, divide by 2 over 2, we'd get 8 over 10, which is 0.8 minutes per lap. So that's our unit rate. Now let's look at the 2.4 minutes per 4 laps. 2.4 divided by 4 is 0.6. So I want you to notice right away that your two unit rates, they are not the same. So one thing we would note is that this is not proportional. And what we would also have to note then is the fact that you are not swimming the same speed for the entire time. Because you slow down after your first 4 laps, we would have to estimate in order to figure out how much time it would take to swim the next 10 laps. If we go with 0.6 minutes per lap, and we multiply that times 10, we would say it would take you 6 minutes. And that's if you continued to swim at 0.6 minutes per lap. But if it took you 0.8 minutes per lap, and we multiply that times 10 laps, you get 8 minutes. So we would be able to estimate that it would take you around, or we would say about, 7 minutes. And really, any estimate that you gave, in my opinion, that's between 6 and 8 would be accurate. However, please understand that your first 4 laps at 0.6 are probably going to be your fastest, meaning that you are going to slow down from there. So thinking that you are going to swim your last 10 laps in anywhere near 6 minutes is probably unrealistic. After making 20 servings of pasta, a chef has used 30 cloves of garlic. The chef used 6 cloves to make the first 4 servings. So how many cloves of garlic are used to make 10 servings? This one is going to set itself up perfectly for making a table. We have pasta and we have garlic. "20 servings of pasta uses 30 cloves of garlic. 4 servings of pasta uses 6 cloves of garlic. So let's first check to see if this is proportional. 20 divided by 5 is 4, and 30 divided by 5 is 6. Okay, so we know this is proportional. Things are working out nicely here. We could also check inside the table if we wanted to. 20 times 1.5 is 30. 4 times 1.5 is 6. Okay, so we're good to go here. So now we want to figure out how many cloves of garlic are used for 10 servings of pasta. Well, to get from 20 to 10, we would divide by 2. So to get from 15 to our cloves of garlic, we would also divide by 2. We would need 15 cloves of garlic for 10 servings. Now it's your turn. Try it on this problem. A runner completes a 25-mile race in 5 hours. The runner completes the first 7.5 miles in an hour and a half. Do these rates form a proportion? Justify your answer, and please do that by creating equivalent proportions or a table. And then, can you determine with certainty the time it took the runner to complete 10 miles? And explain your reasoning. So let's start with 25 miles in 5 hours. Here's miles and hours. So we're going to make our table, 25 miles in 5 hours. And right now I can see that we have an invariant relationship, and we're going to divide 25 by 5 and we get 5. So the runner completes the first 7.5 miles in an hour and a half. So is 7.5 divided by 5 equal to 1.5? 7.5 divided by 5 is in fact 1.5. So we have just proven that we have an invariant relationship, and therefore this is going to be proportional. Furthermore, it's going to tell us that 0 miles would take 0 hours. We're going to have that point in our table, leading us back to the middle of our lesson, where we would look in the table for the point 0, 0 to determine if it's proportional. Now, hopefully this is logically making sense, that if you haven't ran any miles, it shouldn't take you any hours. So do these rates form a proportion? Yes. We can clearly say yes, and the work is right here in our table. Both an invariant relationship and the point 0, 0. Now, can you determine with certainty the time it took the runner to complete 10 miles? You could argue that what you could try to do is you could divide by 5 to get to 5 miles, divide by 5 to get to 1 mile, and then you could actually multiply times 2 to get to 10. So 10 miles could take 2 hours if you did this times 2 and you did that. So you could argue that. However, again, just thinking logically and realistically, it says here with certainty. And no, we cannot determine with certainty the exact time it takes a runner to complete 10 miles, because just like swimming, when you run, you get tired. And a runner's speed varies too much, where you're speeding up and slowing down. So it would be impossible to determine exactly how long it would take to run that 10 miles.